Hi there guys, well welcome back. We've just done 4K, we're about to do 4L, and 4L is all about higher derivatives. So we've differentiated once. What happens when we differentiate again? Can we differentiate again? How many times can we differentiate? What's the meaning of that graphically? Those kind of questions. Now there is a nice investigation here which leads to Leibniz's formula. And I'm going to leave that until the end. I'll talk a bit about that at the end. So talking about sort of generalizations of differentiating many times over. I will basically just deal with the two questions before 4L first. Okay, well, let's just think about what these derivatives are, the next derivatives are. So there we go, some notation which the book is giving you there. Take it up to 200%, why not? Okay, so it's saying, well, your first derivative, f dash of x, is dy dx. If you differentiate again, you can call that f dash dash of x. And that's your second derivative. And then the third derivative, you can call f dash 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 of x. And the way to write that in terms of dy dx is, first of all, dy dx, and then the second derivative is that applied again. So d dx is being applied again to get d squared y dx squared. Okay, and then you're getting similar notation, which is quite clumsy to say, in fact. This third derivative, that's what we would really call it. This d cubed y dx cubed there, or essentially applying d dx 3 times over. Now, because this is getting quite clumsy, we can then say, instead of all these dashes, we can say, let's do it n times over, and then you can write in brackets, as you can see there, f to the n, but that's not a power of n there. That's just saying that. That's just saying we're differentiating this n times. That's what the meaning of that is in a bracket, and as our superscript there. Okay, so there we go. That's what we're seeing as just our definitions at the moment. And they also say that if f of x is differentiable, then f dash of x is the derivative. Similarly, if f dash of x is differentiable, so each time we need to have the previous function being differentiable in order for us to get to the next derivative. Okay, well, let's think about what the meaning is in terms of graphically for these things. I'm sure that the book will go into this later, but I think it's important to get this now to get some sense of why we're doing this. So, you know, this is our original function. You know, the original function might, let's say it's all above the axis. Let's say it's all positive in this defined domain here, domain between here and here. Okay, so there's our f of x. Now, up until this point here, you can see that the f of x is positive. Everything is positive here, but f dash of x in this region, f dash of x is going to be positive. In other words, whatever value of x you put in there, you're going to get out a positive gradient. Now, you can see that up to the next point, turning point here, or these extreme points here, you can see that in this region, right? So in this region here, that's meant to be on that region, we can see that f of x, f dash of x rather, is now less than 0. We have gradients which are all less than 0. There we go, they're all less than 0. Some of them are less steep than others, most steep at this point of inflection here. They're all negative gradients there, so we can say that for whatever value of x we put in, we're getting negative gradients. Now, on the other side, we can see that we've got f dash of x is now greater than 0 again. Okay, we're going, here is 0, and now we're becoming more and more positive in those gradients. Okay, now that's the first derivative. That should be relatively obvious. Now, for the second derivative, that's telling us the rate of change of the gradient. So in other words, is the gradient increasing at this point, or is the gradient decreasing? Okay, well, at this point here, we can see we've got a steep gradient, steep positive, and here it's less steep, but still positive. So it's gone down. Maybe that's a gradient of 5, and now we're at a gradient of 4. And now it goes down again. Maybe this is a gradient of 1, maybe this is a gradient of a half. You can see that your second derivative, the rate of change of the gradient, is decreasing for all of those points. As we go forwards, the gradient is decreasing. It's still positive, but it's decreasing. Now at the top, it's still decreasing because we've gone from 0.5 to 0, and now we're going to minus 0.5. It's still decreasing. In fact, it's decreasing until this point of inflection. Okay, and that's where it becomes its biggest negative value. Okay, or the least value is here. Okay, so until this point of inflection, okay, let's just use some bigger lines there. Until this point, we can see that f dash dash of x is less than 0. The gradient is decreasing until that point. Okay, that's decreasing. Now, after this point here, okay, so that's the biggest negative point that we have, biggest negative gradient, and it starts becoming less steep again. And so it's increasing. Still, it's negative, but it's increasing. And, it's increasing all the way around here, and it keeps increasing there. So on this side, we can say that f dash dash of x is greater than 0. So here, if we want to find our point of inflection, you can see we need to find where we go from decreasing gradients to positive gradients. And so we need to set f dash dash of x equal to 0. Okay, well, that will turn up later, but it gives you a little sense of the meaning of the second derivative. The second derivative tells us about the rate of change of the first derivative. And of course, the third derivative tells us about the rate of change of the second derivative, and so on. Now, that's going to get really difficult to draw on this graph, so I'm not going to do that here. But you get the sense that derivatives are like rates of change, a little bit like displacement is to velocity is to displacement. Velocity is the rate of change of displacement. A bit like acceleration is to velocity. Acceleration is the rate of change of your velocity. Okay, so acceleration would be a second derivative. Okay, just another little thing to mention, that if we wanted to say if we've got dy dx, and we want to apply d dx again, I've said this a couple of times. If we apply d dx to dy dx, so you sort of forget about that now, that's essentially giving us our second derivative. And we'd normally call this our second derivative rather than saying d squared y dx squared. That's a bit cumbersome saying that. We just say this is our second derivative. And of course, that can be written as f dash dash of x if we're using functions notation. Essentially, we're applying this operator a second time. This is like an operator here, d dx. Okay, differentiate with respect to x is d dx. Okay, right, well, let's have a look at the questions then. So let's skip through the investigation. Let's take example 24. And I know that said 1 over x there. Right, so it says find the first three derivatives of this function here. Right, so part A, we've got f dash of x. We're looking for f dash dash of x and f dash 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 of x. And I would probably start putting brackets in after that point there for the up here, of course. So my next one I'll do like this just because it's getting messy. Okay, so f dash of x is just saying, well, times by that 4, reduce the power by 1. The next one is times by that 3, reduce the power by 1, times by that 2, reduce the power by 1. And then we've got a constant term at the end. Constant terms don't add anything to our gradient, it just moves graphs up and down. Okay, differentiate again, and you can see what's happening. You've got 24x squared minus 6x, 6. Differentiate again. Not particularly interesting at this point, but you can see that the function is kind of reducing each time until ultimately we're going to get our derivative is equal to 0, and we can keep differentiating that if we want to, but it's just going to keep giving us 0 after that. Okay, now that's obviously happening because we had natural numbers as our powers of x here. But if we have negative powers, or if we have rational powers, then that's going. This sort of the pattern will continue forever. In fact, okay, but with natural numbers as our leading powers, then it's going to disappear, ultimately, this function. Okay, find the second derivative of this thing here. So we're going to do up B, we're going to do it up here. And we can see that we've got u equals x, and we've got v equals x squared plus 2. And so we know we've got the quotient rule, which we need to use. Remember what that is. Okay, hopefully you've remembered it by now. And there we go. So that's our quotient rule. This is what we're looking for. This is going to give us f dash of x. And it looks like we're going to have to apply this twice here. So, and actually we need to solve an equation here as well. It's not just saying find this second derivative. Say set it equals to 0 and find out the value of x that makes that true. Okay, so what do we got? We've got here we've got u dash is 1, so I'm sort of cheating a little bit here, but v is equal to x squared plus 2, u dash is 1, then minus u, which is x, and v dash is, they're going to be equal to 2x. Okay, now I said I'm sort of cheating, I'm just trying to fit things in here. So let's just write that as 2x squared, and we cheat a little bit more here, I'm sorry about this. Just trying to fit things in. That's obviously going to reduce down to minus x squared plus 2. And take all that back. Okay, so it's minus x squared plus 2. Okay, and then v squared is going to give you this x squared plus 2 squared on the bottom. Okay, so that's going to be our function. And now when we go to differentiate this again, we're going to set up the same thing again. We're going to say u is equal to minus x squared plus 2, and v is equal to, go back a second, v is equal to x squared plus 2 squared. I don't really want to multiply that out, so I can use the chain rule for this one. Now, this time around it's going to be a little less simple, so I'm going to write everything down. So we've got minus 2x there. We've got, what are we doing here? So we're bringing the 2 in front of this thing and times it by the derivative inside, and reducing the power by 1. That's just the chain rule. Okay, reduce the power by 1 times by the 2 and times by the derivative of the thing which is inside. That's just the chain rule. So now we're getting f dash of x, just using the same function as up here. We're going to get our x squared plus 2 squared, and then we've got u dash, which is minus 2x. So let's see if we can put that on the front. Minus 2x there, and then we've got minus and minus this thing here. So maybe let's just extract a minus from this and put a plus there then. So that's going to be x squared minus 2 there. And then we're going to get, so that was, well, we were at u. Now we need to put in v dash. So v dash is this thing here. Okay, well, the x squared minus 2 a little bit further on, so we can put v dash, this bit in front. We've got 4x, and then we've got our x squared plus 2 there. We'll look at the difference of 2 squares there. Okay, now we could simplify this a little bit further, but I don't know whether we shall or not. I mean, we're not actually being asked for a nice expression for f dash dash of x here. And that's a little bit of exam technique here as well, to think, what are we trying to answer? We don't actually need this really nice and neat. We don't need to keep factorizing and make it as neat as possible and try and figure out what that expression is as nice as possible. We just need to think, at the moment, what's our expression for f dash dash of x? And then let's set it equal to 0. So I'm missing something, aren't I? I'm missing my v squared. So v squared, so v is this thing here, and I'm getting x squared plus 2. It seems to be having some issues. Just change pen here, okay? And so we're getting the x squared, and then we had plus 2, and that's going to be squared as well. So that's squared, and then squared again is going to give us to the power of 4. Now the thing is, well, as I was saying a moment ago, that we only need to say, when is this equal to 0? And it's equal to 0 when the denominator is equal to 0. So I don't really care about the numerator here. I care about equaling this to 0? Well, I suppose we might need to actually deal with this one. Okay, well, it's going to get quite messy here, as you can see, and there's a lot of working out. So this would be an algebraic heavy question. But I can see that from that numerator, so what I'm doing here is setting my numerator equal to 0. That's the next bit up here. And I can see that I can take out 2x as a factor from both of these things. Okay, so I can take out 2x as a factor. Okay, and I can also take out x squared plus 2 as a factor. It's in both expressions there. So x squared plus 2. So that's there. Taking that out, I'm taking one of these out. I'm taking a 2x out here, leaving 2. Taking that 2x out here as well. I'm going to write it the other way round this time because this is positive. So I see that I've got x squared minus 2 there. That's my factor from this side. And then on this side, I've still got x squared plus 2. I've got minus x squared plus 2 there. Put my bracket on that one as well. And did I have any extra 2's or anything? I think I had this 2 here, yeah. So I really need to put that 2 in. Sorry about that. Okay, so there's that 2 in there as well. Okay, now I can simplify what's in the bracket. So that factorization does make things slightly easier because then I don't need to do quite so much multiplying out here. There's not really much multiplying out I need to do here as well. So we've got 2x squared minus x squared going to give us just x squared there. And then we're going to get minus 2. And we're going to get minus 4 because there's that 2 there. And minus 4 and then minus another 2 there. Okay, so that's going to give us minus 6. And you know, you can see that this is just algebraic heavy. You probably just skipped on here. Okay, so that's what we're trying to set equal to 0. Now, again, if we're trying to set this equal to 0, okay, if we're trying to solve this equation here, so numerator equal to 0, that's this equal to 0, which leads to which implies this line here. Now we can divide throughout by the 2, no problem. And then we're saying, well, what makes this equal to 0? Well, we've got x is equal to 0 from here. There is nothing from this bracket, no real number from this bracket, which is going to make it equal to 0. And I'm assuming that we're working in terms of real numbers here. So x is equal to 0 makes this one equal to 0. There's this squared here, this bracket here, x squared plus 2 is always a positive function. Think about that one, x squared plus 2. It's like that. You're only getting positive answers out there. So you can't make a 0 from this bracket unless it's a complex number. And then we've got from this bracket, x is equal to the square root of 6, just setting that equal to 0. And that's plus or minus the square root of 6 as well. So there we go. There's our solutions. Find x for this. Let's see if I've made a mistake. No, there we go. Got it right. Okay, I'm expecting a mistake there because there's so much working out and I kind of missed a few steps. So, you know, I'm really pleased when I get the answer right there, just like you guys are as well. Okay. So there we go. Final answer is there. Okay, now part C. Okay, part C says given f of x is equal to this function here, and that was an x on the bottom, wasn't it? And so we're getting that. It says find the second derivative in this case. Now, I'll probably just write this out to start off with in terms of our indices, you know. So writing this one as x to the minus 1. Now we can start doing f dash of x. We're getting here minus 32x, and then this one's becoming plus x to the minus 2. So it's much quicker to work in this kind of index form here. So, you know, what happened there is we times by the minus 1 and we took one off the power. Now, next derivative, we can see that that's just going to become minus 32. And we're going back to minus here, so minus 2 x to the power of minus 3. Okay, so when we need f dash dash of 1, maybe it's easier to rewrite this last expression for x cubed. But let's see. Let's put in the 1. So f dash dash of 1 now gives us minus 32 minus 2 lots of 1 to the minus 3, which is just 1 anyway. So we're getting an answer here of minus 34. Okay, so that one was pretty straightforward. Let's just check that one out. Yeah, minus 34. Okay, so example 25, and then we'll talk about that Leibniz formula a little bit, and the investigation, which was at the front. So example 25 is the last example in this exercise. Let me just take a sip of my tea. It's already getting a bit cold, past its peak temperature. Okay, so example 25 says a particle moves in a straight line so that its position from a fixed point after t seconds is given by this. All right, okay, so this is talking about displacement. S is displacement, and it's in terms of time. This is a t-axis, this is an s-axis. Okay, where s is in centimeters, all right? So find the velocity of the particle at t is equal to 1.5. So we need to find v of t. In other words, we need to find s dash of t. What's s dash of t? The change in s divided by the change in time at that particular instant. It's the average velocity at that particular average velocity. It's instantaneous velocity, sorry. So it's change in s, remember small change in s divided by small change in t. We're looking for our derivative, or the rate in change of our displacement. That's what velocity is, rate of change of our displacement. For example, if we're traveling at 1 meter per second, okay, 1 meters per second, right, if we're traveling at 1 meters per second, that's changing our displacement. It's a change in displacement of 1 positive meter every second. And so we'd be moving forward at 1 meter for every second that we're in motion. Okay, so what have we got? We've got velocity of this particle at time t is 1.5. Find this thing if the velocity of the derivative, if the velocity is the derivative of the position of the function. Okay, well, we've already talked about that. So we're getting here 4 plus 6t minus 3t squared. And now we need to substitute in our 1.5. 1.5, we put that in here. 6 lots 1.5, 9. I might struggle with the next bit. And we're getting 3 lots of, and let's just do this in terms of fractions. So we've got 3 over 2 squared. And so we can see that that's giving us, what's that, 27 over 4. Okay, and now you can obviously simplify that one yourself. Let's see what they're coming up with as the answer. We're getting 6.25. Okay, this is giving us 6.25 meters per second. Remember, m per s is the same as saying ms to the minus 1. That's essentially just taking the reciprocal of s. Okay, so that's v, and if the acceleration is the derivative of the velocity, yeah, so acceleration is the rate of change of your velocity. So, you know, an acceleration of 1 meter per second squared means that our speed is increasing by 1 meters per second every second, or our velocity rather, it's increasing by that. So find the acceleration of the particle at t is equal to 1.5. So we need to find a of 1.5. Okay, well, 1.5 in there, but we're really looking for a of t to start off with. So let's take that back. A of t is then saying differentiate this, getting 6 minus 6t. And then we're putting in our 1.5 here. So 6 minus 6 lots of 1.5. So take away 9 is giving us minus 3 meters per second squared. There we go. So at this particular point, at 1.5 seconds, we can see that the speed is decreasing. So there's deceleration, in fact, of minus 3 meters per second, okay, or meters per second squared. So the velocity is going down by 3 meters per second every second. Now, it's fine to say that this is the acceleration, but if you wanted to talk about deceleration, it would be 3 meters per second squared deceleration. Deceleration incorporates the minus. Okay, right. Let's just check that answer as well. Yeah, so we're getting minus 3 there. Okay, before we go on to the exercise, let's just see what's in the exercise. 9 questions there. And towards the end, it's talking about using Leibniz's theorem. Now, this investigation leads you to Leibniz's formula here. But that's not given in the formula booklet. There's no Leibniz's formula there. And so you wouldn't be expected to use this or expected to know it. But they might build you up in the questions in order for you to get to that point. That would be legitimate. But, that's why they're asking you in the questions, can you use Leibniz's formula? Because they've dealt with it in the investigation that they're expecting you to have looked at. But you're not expected to know this for the exam. Okay, so what are we doing here? This is all about differentiating products multiple times. Okay, now, in fact, this starts off by saying, well, what about if we just differentiate, say, for example, x to the power 4 multiple times? Well, I think we can do a bit better than that. So let's talk about differentiating x to the n multiple times and see what's coming out here. Okay, so let's go x to the n, differentiate it once, we're getting out n x to the n minus 1. Differentiate it again, times by the power, reduce the power by 1. Okay, differentiate it again. You can see really quickly there's this pattern which is building up here, and x to the n minus 3. So there's your pattern as it builds up. And this is our first derivative, this is our second derivative, this is our third derivative in our formula. Okay, now I've just written it like that because it's just a little quicker than writing all my derivative expressions as well. But you can see what's happening. So when we get to our third derivative, we're seeing a pattern here. And you can see that you're getting NPR at the front here. Remember, NPR turned up way back when, I think in chapter 1. There were some counting principles towards the end of chapter 1. And NPR is saying, well, remember that, saying like, for example, remember NPR is n factorial divided by n minus r factorial. Okay, so in this case, you can see that, in fact, that's exactly what we've got. We've got here our formula for NPR. So we've got essentially n factorial divided by n minus 3 factorial. All of n minus 3 factorial is now being cancelled. And we can see that we've got here x to the n minus 3. Now, if we want to then do, so that's our third derivative in this case. Now, if we want our, let's say, rth derivative, you say, then that's also going to give us this n minus r factorial, and then we're getting x n minus r. There we go. Okay, so we can develop these formulas quite quickly, in fact. So there's a formula which is telling us, if we choose to differentiate x to the n, a power of n, many times over, then we can use this formula here. Okay, now you can rewrite this one as NPR if you want, like this, same. Okay, now Leibniz's formula, though, is actually talking about differentiating a UV multiple times over, so a product of functions. Now, it could be that one of those functions is x to the n, and the other function is just 1. So that would be a reduced version, which would give us out, hopefully at least, this formula here. Okay, so let's have a little look at, I've just Googled this. So, So, I mean, if we have a little look at this one, it's saying, well, here's our general formulas on Wikipedia. It's the general Leibniz formula for calculus. And remember, we were talking as well about Leibniz and Newton having this sort of mathematical battle back in their era as well over calculus. And a lot of the calculus notation which we use now was developed by Leibniz. Newton had a different way of writing things down. Okay, so they're talking about doing a second derivative and so on. And then they're talking about the proof here as well. Now, I'm not going to go into the proof here. I don't think the book goes into the proof as well, but you'll be able to see that this is true quite quickly. Now, the proof is a proof by induction. You might be interested in that. If you're a top grade student, you might try and spend half an hour trying to figure that one out. I'm not going to do it here. But let's take our function and let's see what the book there does, because let's see how the book sets up their function. Now they're calling it UV, so I'm going to call it UV as well. So, you know, f of x is equal to UV. F dash of x, we already know, we've already shown, is U dash V plus V dash U. When it comes to f dash dash of x, now our new UV is this. So we're going to need to do U V dash. Okay, for this one, I'm doing this one here. Okay, so I'm taking this. I'm going to say that's U V dash plus U dash dash V. That's the derivative of this thing here. Okay, whereas previously I had U and became U dash. Now I have U dash and it's become U dash there and U dash dash there. I can see I've done it kind of the opposite way around, but hopefully you understand that. When I differentiate this thing here, I've got my original function in the front. See here, I put the original function at the end there. So sorry about that. Maybe I should have written that the other way around. UV dash plus so on, but you know, you get the idea. So if I differentiate, if I say let's take U, let's put it there. Let's take V. Sorry, let's take. So we're going to do U and V dash. You can see I've applied this thing here, the product rule again. Hopefully you see that. So we've got function here and its derivative there, and we've got this function here and its derivative there. There we go. That's a good way of saying it. Okay, we need to do the same for this part as well. And likewise, we're going to get V dash U dash and V dash dash U. Okay, now when we put this together, we can see we've got U dash dash V plus two lots of U dash V dash plus V dash dash U. Recognize anything? The binomial expansion, doesn't it? Okay, now I'm not going to take this further than this. I'm just sort of demonstrating this, but if you do it again, each of these is going to give you two terms. It's going to give you two terms. It's going to give you two terms, and it's going to develop just like the binomial expansion. Okay, so the next one is going to be U dash 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 V plus 3U dash dash V, and so on. Okay, and you can verify that as they're asking you to in the book as well. So we could write this now using f of n. We could say that this is equal to our sigma, so sum of. So we're going to write our binomial theorem in terms of sigma. So our sum of, got NCR. So I'm going to use NCK, I think, to be consistent with Wikipedia and maybe the book. And there we go. I've got n is k up to n, and then we've got u of n and v of n minus k. And those are like your terms from the binomial expansion, except for here, we're not talking about x squared, we're talking about second derivative. Okay, so these are derivatives, they're not squaring, they're not powers on the function, they are the nth derivative or the n minus kth derivative. Okay, well, there we go. That's a quick verification of Leibniz's formula there, which is given in terms of f and g there. And I think they don't finish it off in the book. No, they don't finish it off. They just expect you to have worked to find that. Okay. Well, thanks for listening. Good luck with the exercise. You've got your 9 questions to do there. Good luck with those, and hopefully I'll see you back next time. See you later.